So everything we've done thus far has really been sort of intro to R and intro to like concepts in statistics. So we've talked about models, basic descriptive statistics, and data screening. So now we're getting into hypothesis testing. So we're moving into inferential statistics. And we're starting with the easiest thing first. We are skipping a couple of chapters here and doing ANOVAs and t-tests and then regression. The book has them in a slightly different order. But I find it's easier to start with groups than continuous variables. So we're going to talk about very simple experiments where we only have two levels, two groups, two time points, two somethings. So for that, we're going to have one IV that's categorical. It has only two levels. If we have three or more, that's ANOVA. That's the next set of chapters. If we only have one, it's not really an experiment. So we're going to have at least two levels. That's the categorical variable. That's going to be your IV. One dependent variable, that's interval, ratio, or continuous. So it has to be at least a scale variable in some form for parametric statistics, which is what we're doing. So the most experimental of things would be a IV that's manipulated with an experimental control condition. That would be very traditional experimental methods. And we can analyze those with T. So hopefully t-tests kind of get your feet wet for ANOVAs. And we're going to talk a lot about what the formulas mean today, too. So kind of a warning. T-tests are very easy to analyze, but you should not use them just because you know how to do them. So there's this sometimes problem where people only know how to do a certain set of statistics, and so they manipulate their data to fit those sets, and that's a bad thing. So median split is where you take a continuous variable and you categorize it. That's why I think the grading system is perfectly stupid, because we take continuous variables and lump them into categories. So A, B, C, right? But by doing that, you really cause a type 2 problem usually, not type 1. So here's marker. If you have a continuous set of data, for whatever data, and you just say, okay, I'm going to split these guys down the middle and lump them together, and we'll end up with a bar graph. You're basically saying this person on this side of the Berlin Wall and this person on this other side of the Berlin Wall are different things, even though really there's just a wall in the middle. Okay. So median splits are bad. If we want to use World War II Germany as an example. So separating people that normally are close together. So you lose information, your effect size will normally get smaller, and usually it causes type 2 problems. Okay, that's where you miss it. So don't take a continuous variable and make it categorical just so you can do a t-test. That's kind of the theme here. And then just some quick reminders, kind of stuff from the test and terms that are important again. When you manipulate those levels of the IV, it's an experimental design. If you have two naturally occurring designs, it's quasi-experimental or correlational, okay? And that's the type of research design. Data collection, right, is either between subjects or repeated measures. So between subjects data collection, manipulated or not, is an independent T, and everybody's in separate groups, and they only do one of them. Repeated measures or within subjects are dependent T, is where everybody's in all of the groups, so they do both levels. That is independent, to not use a word repeated. That is a separate issue from the type of design. So I can have between subjects or dependent T that are experiments or correlational designs, and vice versa. Unfortunately, the names overlap, so that gets confusing to people. So independent design is independent T, dependent design is dependent T, sometimes called repeated measures. And that's basically what this slide says. So an independent t-test is two groups of separate people. A dependent t-test is two groups of related people. And in R, the code is actually the same. There's like one spot that you say this is independent or dependent. And so you really have to be careful that you know what type of data you have. The good news is generally you screw this up by doing independent T instead of dependent, and you'll just lose power. Because that would violate the assumption of independence. Right? If it's dependent T and you try an independent t-test, you've forgotten to control for the fact that they're the same people. And so it's not a bad thing about R, but you have to know what type of data you have, which is a general rule, I feel like. But in SPSS, you can't really run it the wrong way. I mean, you can, but hopefully you figure out it's wrong. In R, you can pretty easily. Now, in this book, everything is taught as a linear model, so it actually has code for LM. And we could do it that way, but it's probably a little easier to talk about these in their more traditional formats and use the t.test code instead of using everything as LM, just because it makes the output easier to read and easier to work with. But it's important to know that t-tests and ANOVAs are special types of regression, which is why the book actually has regression first, but I just find it easier to talk about groups first. So anytime you run ANOVA, it's regression, just with categorical variables. So they're special children of linear models. So we could always use the LM function, but instead we're going to use some packages that are designed for each one because that has the information you need. So there's a package called Easy ANOVA that we're going to use for ANOVA. I don't know if it's particularly easy, but it's better than what the book has. Because last year I taught what the book has, and it was fine. It was fine. But then the next semester I figured out an easier way to do it. So to work an example, this is a book example, and it just makes me laugh. Someone was watching too much Harry Potter. But are invisible people mischievous? So we have 24 participants, and this first round we're going to test this as independent T. So it's different groups of people. Some of them we gave invisibility cloaks, some of them we didn't, and we just measured how mischievous they were being, which is the data set that we have. Invisible long, so it's in long format. So each participant has their own row, but in a second we're going to pretend like this is dependent data. Okay, so we're going to actually test the same data set, independent and dependent, and talk about how those things are different. So we have two groups or two levels, cloak versus no cloak. Right. So if I am testing them, a good null hypothesis would be that the number of mischievous acts, which I can't spell that word, so we're going to say acts for cloak. Try that word again. Is equal to no cloak. So basically the cloak has no effect on the acts of the participants. Okay, so equal, no differences. A good research hypothesis is that they're not equal. Cannot spell. Because we don't want to pick a side. I mean, in theory, we probably believe that people who are invisible are going to act worse. Right? So they would have more mischievous acts. But we talked several chapters ago about how most people feel that one-sided or one-tailed tests are cheating. So it could be that since they're invisible, they're just going to watch everybody and they're not going to do anything. So we'll not pick a side and we'll say they're just not equal. All right, so we're going to take those two samples and calculate sample means. Okay. And that's where t-apply comes in. Everybody's favorite t-apply. So remember that t-apply, which hopefully after this last test is a little more solid, is dv, comma, iv, so contiguous, comma, categorical, comma, mean, function, or SD. So let's take a brief second, get some of that stuff loaded up. This code is all on Blackboard. Oops, yeah. I
forgot how to fix that I symbol.
Oh, yeah. Call names.
Oh, yeah, it's just call
names. Data set. Right, square bracket for the first column equals blah, blah, blah. Okay, that's fine. All right, I might have the same issue. Let's see. So if I import our data set here, yeah, I have the same problem. So I first have to fix my data not importing quite correctly. Let's zoom in real quick so it's bigger. There we go. So just what I had on the board: call names, name of the data set, long data, square brackets, 1 for the first column, and it should be capital cloak. It's already factored, which is good, so I don't have to factor it. And my DB is the number of x. So that's a ratio variable because it could be 0. So t_apply the data set does need to be in log format. It cannot be like time 1 and time 2. Right? That's not the way t_apply works. So if at this point you need it to be in long format to calculate the means, you would have to melt it. Okay, ours is already in long format, but there's just a note here that's like, don't forget, you'll have to convert. Okay, so I'm on like 10, 11. We calculate my mean and standard deviation. I'm going to save them because we're going to use them a couple times. So after you save them, just so you can see them, I'm around 13 and 14 here. And so you should get what I have on the slide. Bless you.
Thank you.
So our mischievous ax here runs from 0 to something. Let's just say 12. I'll make this up. One group is at 375. Another group is at 5. So the question becomes, is that different enough? So talk a little more about theory. All of hypothesis testing, I know we went over this before, but this is more of a reminder. All of hypothesis testing is some form of good variance to bad variance. So it's actually a ratio, we're going to use t, of variance caused by the manipulation, something we did, the IV, sometimes called systematic variance, to a ratio of error variance. So ratio of good variance to bad variance. Good variance is the variance we created by manipulating something or measuring 2 different levels if we didn't manipulate it. So we've got no cloak and cloak. Okay. And then there's variance caused by unknown factors. So ability, time of day, personality. In this example, it could be a lot of things. And that we consider error. So we don't know why that's happening. So the question is a ratio of the difference score of 1.25 points more than bad variance? Okay. So is the difference between these two groups more than what we would expect given error? So this is like all the theory stuff, and then we'll get back into how do I do this. So if those two samples came from the same population, we would expect their means to be equal. Equal being roughly the same. So 3.75 and 5 could be the same mathematically. I know they're not literally the same number, but mathematically they're close enough. Okay. And so if they're coming from the same population, meaning the null is true, where those two groups are equal, then I would expect the means to be equal. Theoretically, they could differ by chance. So we would expect these large differences to be very infrequent. Okay. So if they're equal, big differences are pretty rare. This is type 1 error. Okay. If they're equal, that's the big if. So we're going to compare our differences between sample means and compare that to a null hypothesis. So this is why it's called null hypothesis testing. If there's no effect. So we're trying to see if this ratio is different from 0. Because we're comparing this to a null, that there's nothing happening. So we're going to take mean cloak, mean versus mean no cloak. And if the null is true, we expect the means to be equal. If the means are equal, the difference is 0. So effectively, this question is this ratio not 0? Now, not 0 means a lot of different things. It could mean that it needs to be at least 4, a 4-to-1 ratio. It could be that it needs to be at least a 2-to-1 ratio. So not 0 is kind of a range of scores. Now, what are we using for bad variance? So good variance here is going to be mean minus mean. Some form. Bad variance is standard error. Now, standard error for a t-test is actually really complicated, so just get the idea of this is standard error in some form. Yeah, I'll show you the formula here in a minute. So, standard error is what we might expect the error to be based on the population. Okay, so remember, we use standard error because it's our estimate of the population standard deviation. So here's how much the population varies. This is kind of the error we can assume is normal in this distribution. Is the difference between groups bigger than normal variation? So it's really a question of, is this group difference bigger than what we would expect given some normal wiggle around, because people are people. They're weird. Okay. All right. If that difference is bigger than what we would expect, there's two interpretations. Okay. First interpretation is type 1 error, that there's actually no effect, and we've accidentally collected two groups that are atypical of what is real. Okay, that's type 1. Where we say there's an effect, but really there's not one. We just happen to get two means that are pretty different. And that's easy to happen if you have a small sample with outliers. So when we're talking about outliers, a real problem with working with the mean. And that's interesting right now because in psychology we're having this kind of big discussion about a lot of different studies that we don't really believe are true anymore. So some really interesting work on power posing. Y'all heard of all any of this? Power posing with women. There's like power poses. And the researchers who did that research now says, well, maybe some of it's not quite so strong as we thought. And so that is probably more number one. And the effect is not as big as we thought it was. So that's one interpretation. Another interpretation is that there is an effect. The null is incorrect, the research is supported, and those two samples are very different because they're different populations. Okay, so they're different groups of people. So type 1 would be that we just have it wrong. It's just chance. This is power. The two samples are actually different, and we found the difference. Not really getting into type 2 so much. So on the test, we talked about how do I measure my model, and today we're talking about that more as effect size. But as the difference between samples gets bigger, so as these means get further apart, we're more confident that the null is actually false. So our second interpretation here is true. This is science, so use this word loosely. So as the means get bigger, bigger differences between them, we're more likely to believe that they're pretty different. So if the null hypothesis is actually false, we're confident that our means are differ because we impose this manipulation on them. So this is kind of the logic of a t-test. This is actually the logic of most statistics. Good variance, bad variance, and we just implement it in different ways. So here is kind of what I've written already, but observed difference between sample means is mean minus mean. Expected difference, if the null is true, we take that as being 0. So if they're actually the same, then the difference would be 0. Most people don't do tests where you compare it to a number, but you could. So if we were trying to compare GRE scores, we could compare to last year's or something. And then an estimate of some type of standard error. Unfortunately, standard error when you have two samples is kind of ugly. So thank God for computers, because this is what it is. All right, you don't have to know this formula, but this is how we measure independent t. Dependent t is a little different. So we take mean 1 minus mean 2, so this would be cloak minus no cloak. And we calculate this is standard error, and this SP2 thing is down here. So what's happening is we have two groups. We can only have one standard error on the bottom. And it's not really fair to just average the standard deviations, because what if one group is much larger than another? And we average them, we're giving a lot more weight to the smaller group. We just took them and divided by 2. So what this formula does is this is degrees of freedom. This is degrees of freedom down here. Is it weights it. So SP stands for S pooled. So the standard deviations are pooled together, meaning it's a weighted average. So if one group is much bigger than another, then it will weight it towards the group you have more evidence for. So remember, larger groups mean they have more evidence, I'm more confident, so I'm going to put more weight on that score. If I have 10 people in each group, it's an average, is what it reduces to. And then this should look familiar. That is standard error. It's a standard deviation divided by the square root of n. Well, there's 2 of them, so we have to do it twice. If groups are equal, it's just an average score. If groups are unequal, it weights towards the larger group. And so I think out of this, what I want you to get is that the top is a difference in means, and bad variance here, because this is how it's worded on the test, is good variance and bad variance, is a weighted standard error. Okay. So it's a weighted standard deviation, which makes it a weighted standard error. But it's gross. Look at all that math. Usually this time of the semester when I teach this in my introductory stats class, they're all like, "Whoa." I'm like, we're not going to do that by hand. You can see the relief on all their faces. We're going to make the computer do this math. All right. So just a summary of this last slide. So degrees of freedom is this n minus 1 stuff. N minus 1 and n minus 1. So degrees of freedom is actually n minus 1 plus n minus 1. This here is standard deviation. This here is standard error. So this is my, don't forget to talk about this slide. All right, so how do I calculate an independent t in R? All that data screening still applies, and that's really what the example goes over, is data screening. Now in the lab, you won't have to do that, but on the homework you will. So on the example video, we'll cover that, just because we don't have time to do it all together in class. Okay. So with data, independent data or dependent data, univariate and multivariate become the same thing, because we really only have one DV, some measure of mischievousness in this example. And then I almost always do this as multivariate. So I use that code that we did for this test, because they become the same thing, and it's one set of rules for me to remember. Now, if you have independent t all by itself, you only have one column, and Mahalanobis will not run on one column, so you actually have to use z-scores for outliers. But if you have dependent t, you can use Mahalanobis. So on the assignment, you'll be actually able to use Mahalanobis because you have both independent and dependent. And you can screen? What is that word? Screen as one big data. And generally, if I have multiple hypotheses, so like I know in the lab there's 3 different t-tests, but it's one big data set, I'll actually screen the whole thing at once and kind of ignoring hypothesis. That's one way to do it. You can do it by hypothesis as well, it just kind of depends. But I would much rather have more information rather than less, so I always screen like the entire data set at once, okay. Unless it breaks or I have 900 columns, then it's a different problem. Okay, so we're going to use this function t.test. So it's thankfully easy to remember. But this is going to be new. So t.test is actually a special function that just runs a linear model in the background. And so the way it works, and this isn't actually totally new, it's in data screening, but it's kind of, it's that fake regression thing, so it doesn't seem the same. What you do is you do y, whatever y is, so the column for y is approximated by, so that tilde x. So most of the time we think about data as like x and then y. So kind of got to switch that thinking because it's going to be like this all semester. So y is approximated by x. Don't put an equals here. When you set something to equals, you're saying it is this. Tilde means estimate this. Okay, so estimate it, figure it out. I always think of it as like, we'll see what happens, right? That's the way, forever I was like, why isn't it just equals? Well, because otherwise you're setting it to equals. And thankfully none of you have German keyboards. Poor Inga last year doesn't have a tilde on her keyboard. I always hear her cursing right here in the front because she didn't have a tilde on her keyboard. But it's above the tab on the left side. So most of the functions work in this format. T.test, actually, the function will run in a different way. Don't do it that way. This will help you later in the semester if you get into y is approximated by x. Now the nice thing about this is there's no, we've been doing dataset $ column name, dataset $ column name. Now we don't have to. You can just do column. Because it's got a built-in data function. So a lot of the functions we're going to do from now on have this data function, so it tells it where to look. So you can save yourself typing the dataset name 5 or 6 times. So that makes it a little bit faster. var.equal equals true. You can use t or true. So what does that do? That assumes equal variances. We're going to come back to that concept at the very end of the lecture. So for right now, var.equals equals true, so we all get the same answer. And then for independent t, paired equals false. And that should be in all caps if you want to write the whole word. Or if you just want to use the F, you can. So we're turning paired off. Now that's actually the default. And some of this stuff is assumed. But I always find it easier if you just know, like, I always have to tell it this. So you can actually leave paired equals false out, but then later, if you're like, wait, what was the command for dependent t? It just helps if you remember which one you're doing. So independent t, paired is false. All right, so this is the application for the data set we're using. Right? So db is approximated by groups. If you switch this, it doesn't always give you an error, but it definitely like bars. So I'll tell you that in a second. Data equals data set. Var is true, paired is false. So don't switch them, I guess would be my answer. Okay, so let's see here. So I'm going to run the real one, and you should get this 2 sample. It should say 2 sample t across the top. If it says Welch, you've done the wrong one. Now let me show you what happens if you run it backwards. How do I spell that? There we go. Okay. Oh, good, it does give you an error. Some of them don't. Some of them run and give you the wrong thing. So it says grouping factor must have exactly 2 levels. That means you have them backwards. If you run them backwards. So db approximated by iv, data. If you leave off this var.equals thing, at the top it'll say Welch 2 sample t. So you want to make sure Welch is not there. The degrees of freedom will also look funny because they're partial degrees of freedom, and we'll get into what that actually is doing at, like I said, at the very end of the lecture. Right now, though, we're going to stick with the regular old 2 sample t-test. So it says mischief by cloak, so y by x. Here's my t-score. So this is the ratio of good variance to bad variance. So mean differences over standard error. So I have a 1.71 ratio. So should I believe that score? I don't know. Gives me my degrees of freedom. Now degrees of freedom are n-1 plus n-1. So we've got 2 groups. So it's still n-1. But now it's n-1 for group 1, n-1 for group 2. So 12 minus 2, 22. and then my p-value. And we haven't really gotten into this too much, so we'll get there in just a second. But I also like that really nicely here. It says the alternative hypothesis, the true means are not equal to 0. So it's telling you what hypothesis it's running, because you can actually change that. The next thing down is the confidence interval of the difference score. So that is a confidence interval around 1.25, so 5 minus 3.75. And then it actually gives you your sample means. So we ran the sample means a minute ago, but it helps if you check. So you don't want your sample means to be different from your t-apply. Something's gone wrong. All right, so this question, how do I determine if this ratio for t is good enough? So the t-distribution is very similar to z. It's centered over 0. It's set in standard deviation units. Right? It's actually probably standard error units, but units of standardized units. And the 0 point indicates the null. So most of these results are going to be very close to 0 because there aren't real differences and we're wrong. Because remember, we want to only reject things that are actually truly different. And we have our little race car. And we have to have some sort of cutoff line in the sand for when we would want to reject the null. And we talked about that being p less than 0.05. So that's actually alpha is less than 0.05. So we kind of split the difference, 0.2-0.5% on each side. Now, in introductory stats, we make them learn how to use a table, and they have to figure out what's the cutoff score here. We talk a lot about lines in the sand. But the idea really is this ratio, good variance to bad variance, large enough for me to say, yes, these are different? And the way that we do that is not by looking up what the large enough ratio would be, although we could. Instead, we look at the probability of that ratio. So this p-value out here is the likelihood of that ratio. It's an exact probability. And that probability is about 10%. We've decided that 5% is the rule, so this would not be significant. Our car gave up, and it's not significant. Okay. Well, most of you are used to thinking about p-values in this way if you've had stats recently. It's the first thing people look for is p less than 0.05. All right, so I don't know how you learned how to do this in your research methods class, but we put exact p. Yeah, that's APA 5 actually. So anytime people tell me, oh, it's p less than p less or p greater than 0.05, I'm like, do you know how many numbers there are out there that are greater than 0.05? A lot. So exact p values. But I mean, I could look this up. If you give me enough information, I could pull a table and look this up, or I could type it into R. And what's interesting about that, having these numbers, is that you can actually check and people have done their statistics right. And it's actually happening right now, so this is really just like a total aside that's really interesting. And then, is they have this little like program that's like crawling people's publications and posting whether or not their statistics are right. And so this is kind of like becoming a big issue because people are, I guess, afraid of being called liars. It's a lot of posturing going on right now. But I had like just heard about this, that there's this thing that's like finding all these articles and posting on them whether or not they're correct. And then literally I heard about it, and the next day I got an email that one of mine had been done, and I was like, oh God. Happy to say a weird article for this to happen to because it was actually not really a big, like it wasn't an experiment design, but I have to say I passed. But it is true. I mean, I can take your numbers and look them up. And there have been times that I've been reading things where I've been like, how did they get this number? Like, the numbers don't add up. And so right now there's a big push for statistical reporting that is correct. So talking about, did you eliminate outliers? If so, how many, so I can understand where your degrees of freedom are coming from. So reporting them. So this is T Right, this is df here equals t, p equals p. So this would be the correct way to report it. Okay. Now, I can use p, so we'll get through effect size and we'll take a quick break. I can use p-values to determine if it's statistically significant. But for me, especially, statistical significance is it depends on a lot of things: sample size, power, alpha. So there's a lot that goes into that, and it doesn't necessarily mean practically important. So significance to me is sort of like, why are we talking about this still? So we're going to do a lot of effect sizes. You can ask for here. All the effect sizes. Because to me, that's where it's more interesting. So it might be that something is significant, but not practically important, or vice versa. So a reminder, we talked earlier in the year about the aspirin studies. Those are not significant, but very big effect sizes, which is why they tell you to take aspirin if you think you're having a heart attack. The original seatbelt studies on whether or not your life will be saved. Big effect sizes, not significant. So I think there's a push right now to switch from focusing on P, which is so temperamental, to focusing more on effect sizes. So a couple options. We're really going to focus on D, but Cohen's D is the most popular. It's a Z-score. And then two alternatives to Cohen's D: Hedges G, which is just a correction on Cohen's D. So it's actually Cohen's D plus a population correction, which I'm not showing the math for because it's gross. And then Glass's delta. So delta is Cohen's D, but for control groups. So they're just different forms of D. So to remind you what D is. So it's a ratio of good variance to standard deviation. Okay, and in an independent t-test, that's the formula. T is good variance to standard error. So D is always less than T. Okay, unless they're both 0. Okay, absolute value-wise, it's always less. Though you can get negative scores, that's fine. It doesn't really mean negative. And so why is it always less? Well, pooled standard error is always smaller than pooled standard deviation. Right? Because standard error is standard deviation divided by n. Okay, so standard error is always smaller, so that makes this number always larger. So if you get a effect size that's larger than T, magic has happened. It shouldn't happen. But if you think about the changes in these formulas, what is happening? Well, standard error is based on sample size. Okay. So it's got sample size in it again. In some form, depends on independent T or dependent T or Z or whatever. It's the expected standard deviation given that sample size. So in theory, effect size is removed from sample size. Now in practice, that's not totally true because outliers still matter. But in theory, D is a little less sensitive to sample size in a perfect world. Hedges G, Glass's delta are just different forms of D, so they have the same issues. You can also do R. I would tell you that is not popular. The book talks about it like it's something that everybody does. It's such a lie. I would say you're going to see Cohen's D. If they have an effect size at all, it's probably going to be D for T or, t-test, post hocs. So we're going to go with D. Now, the effect size script that's on Blackboard has all three of those. It has all four, actually, but mostly you're just going to talk about how to work D. So, open both scripts, but don't really look at one of them, because it's a little scary. So let me show you. So there's calculate.r and fsize.r. Really, you just need fsize.r. So what fsize.r it has in it is calculations for a lot of effect sizes. Okay, this script will work for us all year and then some. So it has functions for a bunch of stuff. It's really long. Don't edit that one. So what you do is you open it up, you highlight everything. So I would hit Control A because that would highlight everything. Or I think run all is one of these options and run the whole thing. It will take a minute to run. When you do, you should get a whole bunch of crap over here. And that's what we need. So it's not a package because I haven't done that part yet. So it's not like a library you can load, but the idea is the same. Like anytime you close R and you don't have those functions anymore, you're going to have to rerun this to get them back. Okay. So it's kind of like a package. Calculate.R has more of the explanations. It has examples of every single type that you can do in this package. So for right now, I'm going to give you guys the example that you need specifically for this test in the code. So it's already in our code for class today. But later, if you're like, oh, which one was that? This is the one that has like all the different types that you can do and what they're supposed to look like when you run them. Okay. All right. And it's also got more explanation up here of what everything is. So I'm going to go back to my two means. Here. So it's just like a library. You're going to have to run it every time you open R, unless you save the workspace. And the function we're going to use is d.independent. That's what we're doing. But to get there, I have to have mean, standard deviation, and n. We have the mean and the standard deviation from earlier, but now we need n. If you didn't know, it was 12 and 12. Okay. Remember, we can use tapply and do the length function. Okay. So really, this little section right here is just so that you have the numbers you need. Okay, so I know there's 12 people in each group, my means and standard deviations. And then unfortunately, I haven't come up with a good solution on how to make this not manual typing. Just have to type it. But mean 1 is 5, mean 2 is 3.275, my two standard deviations, don't mix and match. Okay, so make sure you have them lined up. My ends, so that's hopefully fairly obvious what those are. The next two pieces here, a equals 0.05, that's alpha. That's our type 1 error rate. So we could change that to be 0.01, and it would tell you whether or not it's still significant. Pretty much you're going to leave that 0.05 all year, because that's what criteria we're using as our line in the sand. K is the number of decimals. So you can change it to 3. 2 is a good one. So I'm going to run that. You're going to have a glorious moment, because it outputs it for you in APA style. So it's really not an excuse for not having it correct in anything you do in APA style. Yeah. So it gives me my mean. These are the numbers you enter. This is standard error for each group separately. So that's this standard deviation divided by the square root of n for that group by itself. It's not pooled standard error. It gives me the confidence interval for that group by itself. Okay, so that confidence interval stuff that you guys did before, now applied to t. Then it gives me my t-test, actually. So we've actually already run t's. This is a good way to check, make sure you've done something correctly. Both of them show up the same. So my t-test here, my p-value. Here's Cohen's d, right? So it's 0.7. And then it gives you the confidence interval for d. Okay, so this last confidence interval is for the effect size. And that's really because I use a script to do meta-analyses. And for those, you calculate the effect size and their confidence intervals. So we're calculating confidence on effect size. So the confidence on this effect size runs from basically negative to positive. And so I don't know how much I should believe this effect, because the effect size crosses 0. So yes, it's close to a large effect. It's 2, 5, and 8. So it's somewhere between medium and large. But the confidence interval for that effect size includes 0. So I don't know how confident I should be in this. And then if I look at the confidence intervals of the means, they overlap. So it's not significant. The effect size, while fairly large, their confidence interval includes 0. And the confidence intervals for the means overlap. So this is really pointing towards not significant. Okay. All right. one last thing, we'll stop at independent t and take a break, and then we'll do dependent t. Oh, you will get this warning. I put this on purpose. This warning happens every once in a while. You have not done anything wrong. It just is not happy that it didn't get to a very precise level of confidence for the confidence interval. It's a really long story that you don't want to hear, so just ignore it. Okay, the numbers are still correct. The confidence interval for D might be just like tenths of a decimal wrong. And that'll happen with very small t values or very large t values. So it has a hard time figuring out what the confidence interval for D should be if t is really small or really large. Like if your t is over 12, it like totally freaks out. Okay. It's like, I don't know what to do, this is so big. Okay. All right, so we didn't get a significant effect, but we found a medium effect size. So how many participants would we actually need to find a significant effect? So normally you do power at the beginning, but this is like a good place to talk about it. So we're going to open up Gpower. So we're going to do t.test family. The statistical test is means differences between two independent means. This is what you actually did on the test. But now really for t-test. Two tails. You don't have to calculate the effect size, you just fill it in, so 0.7. Alpha and power aren't going to change. In our case, allocation is 1 because n is 12 and 12. And to do that, you should get what I have on the screen is 68 people. So be sure tails is 2. It defaults to 1. I don't know why. T-test, differences between means. I don't have to even hit determine because I've found the effect size from something else, 0.7. And I need 68 people. We have 24. We're way underpowered. So we really need more people to find this effect. So how might I report this? Well, I need at least my means and my standard deviations. So here's what those look like. Participants who were given a cloak were engaging in more acts, but it's not significant. So this difference was not significant. However, it does represent a medium effect. So what are we going to look for on your homework? You're going to look for means and standard deviations or standard error. But means and standard something. T, P, and D. It rhymes. So you need all three of them. So t-test, p-values, and the effect size. You can use, whoa, that's huge. Scroll out some. You can use this stuff directly from the effect size output and use those to cut and paste because that's going to be in the right format. This is a little more information than you need, but it's better than not having the information you need. Like I said, this is in APA style with square brackets and everything.